Good. All right, cool. Yeah, so these industrial business zones are full of material, activity, and lack green infrastructure. But unlike other parts of the city, there's a lot of potential here, right? Because you're looking at areas that are zoned strictly for industrial use, right? So we really can't, it kind of eliminates the possibility of, if we were to implement more green infrastructure, we wouldn't have the full-fledged green gentrification in these areas, right? These IBZs create like a natural buffer and really provide like potential for real community assets, as far as like compared to Gowanus, where we're seeing tons of residential development and kind of lack of that consistent public amenity. All right, so and we can see like the industrial workforce is also very similar to the demographics that we talk about when we're talking about urban heat island, right? So what they've been doing all summer is really studying how we protect these demographics at work, right? As opposed to just cooling their homes at night, right? But yeah, so there were tons of challenges. They went out day in, day out. It was hot every day. They came back sweaty every day. Tons of rain, and just like finding like cool spots in the IBZ in your study time was not easy. But it's been a really great time. I want to thank everybody, all this like specialists and everybody who contributed, the whole entire NCA staff. It's been great. And as well as just like you guys, I hope you all recognize when you're listening to their work, they did this all in 6 weeks, right? So they learned about NCA and then they turned out a study in like 4 weeks, right? So they had to learn a lot in a very little, with a lot of time constraints. So I'm very excited for you all to very excited for you all to share your work with everyone else. And this is the order of our presentation. And with that, we'll kind of get it started. Yeah. Yeah, I got that stuff. Sorry.
Does anyone have glare from the? No, it's fine.
Hello, my name is Sophia. My research will be focused on understanding the capacity for green infrastructure in the Maspeth IBZ, especially as it relates to green roofs. So our agenda will be taking a brief introduction, mostly what Musa already said about UHI and IBZs, our existing policies for green roofs, my research question, the methods and materials, the results of discussion, our conclusions, and then the references. So most of this was already covered. The urban heat island effect is from high concentration of concrete and other heat retaining materials in urban environments. The lack of soil and green spaces, which the soil retains water and can cool surrounding areas. And also the layout of the city amplifies the urban heat island effect and can cause health-related issues as higher temperatures linger longer during extreme heat events. In industrial zones in particular, this effect is amplified because of higher levels of anthropogenic heat generation from industry and from all the trucking, and as well as the lack of green infrastructure and canopy cover. There are a lot of challenges that come with trying to add green infrastructure in IBZs, and for a brief rundown of green infrastructures, we're talking about like rain gardens, green roofs, and just adding trees to the area. The street layouts are somewhat unconventional, and this can make installation of bioswales or rain gardens and the planting of trees difficult because they're often designed to fit into city standards. Additionally, businesses are concerned about liability. So adding a patch of vegetation where someone could potentially hurt themselves and lead to like workplace suits is something that they don't really want. Also, there are high upfront costs and maintenance costs that come with adding green infrastructure, even though it's been showing in the long term that the benefit that comes from stormwater, retaining stormwater levels out. And also green infrastructure tends to take up a lot more space than conventional gray infrastructure. Finally, it's really hard to pitch the health benefits of adding vegetation because the people who work in the IBZs, or there are people who work in the IBZs, but there aren't like permanent residents. New York's existing green infrastructure policy for green roofs and bioswales, the DEP installs bioswales wherever it can as part of its stormwater mitigation program. And there are incentives for green infrastructure as part of New York's Green Roof Abatement Program and Green Infrastructure Grant. And recently, because of Local Law 92 and 94, any major renovations or new constructions are required to have solar installations or green roofs. My research question focused on how the efforts to implement green infrastructure in industrial business zones can most effectively complement the interests of the businesses in the area. And then additionally, I focused on green roofs because in addition to the cooling from the evapotranspiration from the plants, they also have insulative properties that could be beneficial from a cost standpoint. A green roof system that's 4 to 5 inches deep is approximately 30% has a 30% higher higher insulative properties than a conventional roof system. Even though this is a little bit hard to measure because the U values and R values that we typically measure insulation in aren't great for green roofs because they typically focus on like the worst scenario. Still, there's like dynamic modeling to see the insulation benefits of green roofs because it can depend on like the climate, the type of substrate, the vegetation. Also, green roofs are less intrusive, and a Maspeth has very large lot sizes, and the bigger the green roof, the more cost effective it is to install it. I took a 3-pronged approach to this research question, identifying the existing conditions and categorizing the businesses existing in the IBZ, sorting lots based on their potential for green infrastructure. I took a look at the policy in the past and present, the success of solar panel initiatives, the current Local Law 97 rollout, and how New York plans to address extreme heat and green infrastructure going forward. Additionally, I plan to use these to formulate questions for a questionnaire to get input from workers, business owners, and property owners, all which have a stake in this. The tools I used were Google Forms, create and distribute questionnaires, Google Earth and Maps to locate and identify companies and businesses, ArcGIS to gather and plot geospatial information on locations in the IBZ, and also Excel/Google Sheets to collate, sort the lot sizes, the locations, and also contact information. Our methodology involved policy review, first identifying and reviewing policy based on the urban heat island and extreme heat with mentions of green infrastructure, and comparing it with solar panels, PV, and energy. Sorting through the land use, I obtained the tax lot data from Map Pluto, which is publicly available. And then I overlaid the IBZ map to filter out Maspeth and extracted that to Excel. And then I sorted and removed the streets, parking lots, and all the other stuff. And then was able to cross-reference that with Google Earth for the names and the existing PV infrastructure. I found roof area based on the building area, the floor numbers, and where that wasn't possible because of sometimes the data had building area of 0. I used the floor area ratio and then the lot area and found the building area that way. And then this refined data set was used for a PV map and also to find locations with potential. Here is an image of the tax lot map, and this is our zone Maspeth, which we were studying. The results, the factors that I looked at were first the type of building use and then the ownership, because in many of these, especially in the very large buildings, there were multiple companies, and this was all different from whoever owned the property. So these were all competing interests that we had to take into account, or that we will have to take into account if we're approaching anyone on whether on a green roof installation. Additionally, specs such as the building height, the building age, and the structure type also come into account when discussing a green roof. And for the roof itself, whether or not there is existing infrastructure there, for example, like a sawtooth canopy that you can't really get rid of or work around, the area and the depth. So for the locations, we managed to identify and document 484 businesses in approximately 300 lots. 72 of these lots contained multiple businesses. The inferred roof area, again, I found using that, and I found that there were 42 roofs that had an area of greater than 50,000 square feet and 100 with a roof area over 20,000 square feet. This is significant because the New York grant for green roofs scales with roof area, with the minimum required for the grant being 5,000 square feet, and then scaling all the way up in steps to 20,000 square feet. The solar panel distribution I also found, and I found that out of the 42 buildings with an area over 50,000 square feet, 11 have existing PV installations. This can be taken like two ways. First of all, if they already have existing installations, there's a lower chance that they would be open to a green roof because they already have stuff on their roof. But also they might be more environmentally conscious, and it might indicate, especially because these large buildings have so many companies within them, it might indicate that this type of these type of businesses are willing to work together, and there are benefits for the owner aside from that. And this is the same data visualized with the other factors. For lot use, there was a lot of like parking lots or scrap yards, metal yards. Those are like in the other category. But still, if we don't look at those, a majority of the lots are single businesses. The inferred roof areas, a good portion of them are really big, which is signals a lot of potential. With let's see, with almost half having between 5,000 and 20,000 square feet of roof area. For lot sizes over 50,000 square feet, over half of them did not have other roof infrastructure. About a quarter had solar panels installed, and the other ones were either being used for other purposes or they were something like a metal yard, which wasn't a building lot. This is a map of the solar sites. Oops, the solar sites in the IBZ. It's a little faint, but they're the green outlines. Still, you can see there's a lot of space and a lot of potential. Here are my possible sources of error. I did have to sort through a couple hundred entries. And so I could have miscounted, or I could have accidentally skipped a line. Future changes such as planned installations or construction are still unknown. And also with the speculation about increasing real estate prices, the profile of the buildings in the area might change rapidly in the coming years. Additionally, smaller businesses without an online presence or obvious signage, as we were walking around, could be left unaccounted for, given we managed to only identify approximately 60% of the 850 businesses Musa talked about. And also, just from the data standpoint, sometimes because Map Pluto took from different city sources for tax data, sometimes in the address entry, there wasn't what we would think of as a complete address. And so there's something like just 55th Street, which has a lot assigned to it, but it only has the name of the street in the address category. And that made identifying what lot it was specifically a little bit difficult, because if you put in 55th Street, it'll spit out street or a bunch of things on 55th Street. Finally, what we can learn from the past, based on the solar initiatives and the CO2 emission initiatives, and how we can use this for addressing the urban heat island. There are a variety of state and city programs for solar and energy efficiency. And to an extent, this is present for green roofs when it comes to addressing the urban heat island. I think it's important to focus on the paths for communication, especially because for solar, you can see, you might be able to see there's still advertisements for solar panels, incentives for selling back to the energy grid. And this can be, solar panels can be arranged really easily with your energy company. For energy emissions, with the implementation of, or the coming implementation of Local Law 97, the city has worked really hard to establish really clear guidelines for enforcing it. So there are carbon coefficients for the fuel source, the heating, cooling, and you can use these numbers to really identify how you're doing when it comes to your building's energy efficiency. Additionally, there are education efforts for informing people on their other options, so RECs and different incentives. Additionally, for both of these previous and solar was successful, we'll see about Local Law 97, but it's shaping up to be, pretty clear. There are a lot of readily available and accessible resources. Online, there are cost calculators and emission calculators. There are rooftop suitability maps for solar panels, and then also guides from NYC Accelerator and the Energy Star rating for your CO2 emissions. So I think prioritizing accessibility, especially because green roofs are a little bit more difficult to calculate the benefits of. So making a very streamlined and clear metric for that, I think, is important. And then also setting tangible goals, which you can see for solar, and for energy emissions, they have a set number by set year. Oops. And so this is a little summary. There's a large potential, a lot of lots that are over 5,000 square feet. At least half of the ones that are really big have roof potential. There's a need for communications because it is difficult to exactly quantify cost benefits of green infrastructure. But hopefully looking through factors such as this can help. Additionally, business interests and land ownership adds additional complications. Finally, for future study, because I have all this data gathered and contact information, it could be used for future outreach, or it could be analyzed through the building age and the materials, because the tax lots were also connected to the Sanborn maps, which had the building materials in them, or at least they did from a while ago. Finally, I had planned for there to be a survey involved in this research. Unfortunately, due to time, I couldn't get any responses, but lessons learned, I learned about how to formulate questions for the general public. Also, just trying to do street level interviews. There were very few people walking around the IBZ. Like, we talked about how the roads weren't necessarily very accessible, but that also means for the people working there too. So most people drive in and out to work, or they take the bus. Phone numbers for these businesses are more readily available than their emails, from what I found online. But it's also very difficult to think, if you think about like trying to call up a business that are like in operations. So you wouldn't want to interfere with that. And these are my references. I didn't know that was so quick. Anyways, these are my references, and thank you.
All right, hi, I'm Mohamed.
I'm Alexis.
And going into our research project, we had a big general question in mind, and that was what opportunities for green infrastructure exist in the Maspeth IBZ. And so we use that as our general question for looking into the IBZ and determining these spaces.
So this is our table of contents. We're going to take you through a little bit of background information about UHI. We're going to tell you how we chose our sites and how we collected our data, take you through each of the sites, and then finally give you a little bit of a summary. So you're going to hear this a billion times, but UHI is defined as the phenomenon of increased and more intense temperatures in cities. This effect is particularly strong in industrial business zones for a few reasons, but we're going to focus on mainly 4. So there are very large lot sizes in the IBZ. Lot sizes have very dark surfaces. So when the sun emits light, it emits it as ultraviolet radiation. Ultraviolet radiation is a short wave, and when it hits a lighter surface, this short wave bounces back again and it maintains its short wavedness. However, when it hits a darker surface, because darker surfaces lack this reflectivity property, the wave slows down almost, you could think about it, and it turns into infrared. Infrared is just the name of the wavelength of heat. So therefore, darker surfaces are a lot hotter than lighter surfaces. There's also very little vegetation in the IBZ. Plants go through a process called evapotranspiration. This is just evaporation and transpiration. Transpiration is just like a special plant evaporation almost. So during evaporation, water molecules will absorb the energy around it in order to become water vapor. So this process cools the area around it. Additionally, there's a lot of pollution in the IBZ due to anthropogenic or human activities. So within the air, there's a lot of greenhouse gases, things like CO2. We know CO2 is a greenhouse gas, so therefore it's trapping a lot of energy and not allowing it to disperse. And we end up producing a lot of the CO2 from manufacturing and activity in the industry. However, one of our goals with this project is to preserve industry within the Maspeth IBZ. Musa pointed out that these areas are essentially New York City's backbone in the economic sector. So rather than try to stop these activities, we just want to be able to mitigate the effects of urban heat island for the people who are working within them. So one of the ways to do this is through green infrastructure. We have a gorgeous green roof out here today. Green roofs are great at dispersing thermal energy because of that evapotranspiration process. They can reduce temperatures by 2 to 9 degrees Fahrenheit. Pollinator pathways provide habitat for pollinators, bees, butterflies, even birds. And you lack a lot of that space within a city. Rain gardens are used to enhance stormwater management during cloud bursts or very heavy sudden downpours. This water, or rather I should say, our stormwater system gets very overwhelmed, and the water collects over impermeable surfaces like asphalt and concrete. So rain gardens are used to sort of hold the water and prevent further erosion.
And one of our main focuses of this project was also canopy cover and shading of the IBC. So one of the most important things are shade trees. And what a shade tree is it's basically a tree that's usually large and it provides shade to the surrounding environment from its crown. And what the crown is, as you can see there, it's all the above ground parts of a tree. So its stem, its branches, and its leaves. And canopy is just a collection of a multitude of crowns. And how we looked at all this was we looked at the publicly accessible NYC tree maps in our sites and counted the amount of trees and looked at what they were. And going into our methodology and how we went about collecting data, our first thing was there's not much shade in the IBZ, and any of it is usually accidental. It's not a purposeful type of shading that trees were planted and they're meant to provide cooling for the people around. No, it's usually just from buildings. And as the sun moves throughout the day, the shading switches up. Buses are probably one of the main commuter things in the IBZ, and there's not that many shaded bus shelters throughout the IBZ, so we can't really rely on those to be anything for commuters waiting. Like there, even if it's a narrow strip of shade, they'll still choose the shade. And some buses just don't have any shade at all, so people are forced to stand in the heat and possibly face exhaustion for that. And just a general look on bus ridership in the IBZ. This is throughout the month of July, and you can find this on the MTA's website very easily. And those four up there are the buses that run throughout the IBZ. They all generally run throughout the eastern section of the IBZ. And you can see that as sometimes the bus ridership goes up to 6,000. Now this is for the entire bus line, but you get a general outlook at how many people just ride that specific bus throughout the day. And we mapped out all the bus stops in IBZ. Like I said earlier, they're all throughout the eastern section mainly. And most people actually would drive into the IBZ. So our project focused on the people commuting there, whether it's mainly through walking after getting off of these bus stops. But all three of our sites that you'll see in the next slide, we all chose them, and they all ended up being relatively close to bus stops. See it in the next slide afterwards. So going into this and choosing our sites, we can't just go in there and just put a tree on every block we see. We have to choose ideal areas in the IBZ for green infrastructure. So these can be areas that already have green areas in there, but they're not purposeful green areas. They're just there. Stuff is just growing. And we have to make sure that we're not blocking any businesses. So we can't just go into a random truck distribution center and just put a tree in front of the parking lot, right? And we have to make sure there's walking space for the people there. There's no point of putting a tree if no one can walk in that area. And so we have to keep all of these in mind when choosing our sites. And so with keeping that in mind, we ended up choosing 3 sites, one at Grand Avenue, one at 56th Terrace, and one at 49th Street. All of these being potential areas for green infrastructure and not disturbing any business owners. Thank you. And so we measured all these variables, the time of day. We chose 2 time slots, one at 12, sun is at its peak, and one at 4, which is around peak hours for workers who are leaving work. It's usually when it begins. We looked at surface type, so whether it was asphalt, concrete, soil. We looked at surface temperature and we measured that with heat guns, air temperature and air quality with a quality test kit. Shade percentage, we measured out the amount of shade using tape measure. And tree count, again, NYC tree maps, and foot traffic. We just counted the amount of people walking throughout each site and also their behaviors, such as if they were street crossing to find shade, if they were visibly exhausted from the heat, which we saw a lot of.
And we did the foot traffic over a 15-minute period. So this is our first site. It's Grand Avenue. It's located nearby the Maspeth bus depot. On the left-hand side out of view is Grand Street Bridge. There's also the Q59 bus stop, Grand Avenue and 47th Street stop. So you get a lot of vehicle traffic, a lot of bus traffic, especially in this area. And you actually do get a surprising amount of people walking by and waiting for the bus.
And again, just the one tree on the entire block was counted with, and you can see an elderly lady where they're waiting for the bus in the shade. And you can't see it because I cut off the image, but there's around 6 people in that bus shelter. It goes to show you that there's not much shade and people would rather cram into one tiny area to find shade than wait in the heat for bus stop. And it was very hot on that day. It was during that 2-day heat wave. So. And these are just 2 pictures. It's blocked by the little thing on the bottom, but this was at 12 p.m. So you can see that a lot of the shade is from the building and all the way back there from the little tree. But most of the shade is just from the building, and it does cover a majority of the block, which is nice. But as you'll see in the next slide, it changes throughout the day, right? As the sun moves throughout the day, now the building isn't shading much of anything. And so now people are exposed to the heat basically everywhere on this block. And yeah, just a quick segue into daylight analysis. So I took a picture of the sun up there just to show where exactly it was. If you can visualize it, it would be to the other side over there, to the other side of the building. And that allows the building to provide shade for the people. But now it's directly head on. And now you really can't find any shade on that entire area. And this specific phenomenon, I guess, is present throughout all 3 sites.
So this is a map of the shade coverage of the area at 12 p.m. specifically. So, or not at 12 p.m. specifically, at Grand Avenue specifically. At 12 p.m. you see it has a shade coverage of 60%. So like we said, the building is providing a lot of shade. But at 4 p.m. it drops all the way down to 5%. And this shade is completely inaccessible. If you notice within the photos, there's a little bit of plant space and vegetation pushed all the way up against the building. So that's where the shade comes from, but there's no way to walk beneath it, and it provides no real benefit to people. Oh, and in the map, 12 p.m. is marked by red, 4 p.m. is marked by blue. These are not indicators of temperature. It's just so they stand out to you.
And going into foot traffic patterns at Grand Avenue, again, we measured it over a 15-minute period. And so that amount of people that were there at 12 p.m. was, the average was around 8.5, with it being 7 at 4 p.m. So not much of a difference. And so the dominant behaviors, people were seeking shade along the sidewalk at 12 p.m. because that was the time there was shade. And then underneath the bus stop and the tree canopy being the only 2 places with accessible shade on the block at 4 p.m. And they're all waiting for the bus. And the blue arrows show the dominant places where people walk.
And you can see in the blue circle, that's the hot spot where people waited. That was where the bus stop was with the shade. And in this graph here, you can see unshaded versus shaded surface temperatures. The unshaded surface temperatures are significantly higher than the shaded. I also just want to note the axis at the bottom is not 0, it's 50. So you can see how asphalt, a dark surface, retains more heat than, say, soil or even concrete. The air temperature in this instance, it was 12 p.m., it's 91 degrees. The asphalt is well above 100 degrees. Decrepit asphalt was just very broken down asphalt. It was very washed out and gray. And because we talk about light versus dark surfaces, we wanted to make that distinction. But in general here, you can see how much hotter unshaded surfaces are than shaded surfaces. And then this is just at 4 p.m. So air temperature is 96 degrees, asphalt, the decrepit asphalt, and even the concrete are all above 100, with the soil being below the air temperature. So this is our second site, 56th Terrace. This site is a little more isolated from heavy industrial activity. You still get a lot of trucks coming through. There's a lot of loading and unloading of things. But in terms of someplace like our first site where you have the bus depot, it's a little bit more low-key.
And again, just a general tree map. I'm not gonna bore you and sit here and count every single tree and give you its name. But the mainly the notable one is the thornless honey locust tree, which is a shade tree. Does provide a lot of shade in the area, and you can see the 6 of them. Those are the big, like light green. Point out one. It's these ones over here. So. Just pictures of the area. As you can see at 12 p.m. the shade is from the trees. There's not much shade at all from the building. It's just that tiny little strip right there near the building, but most of the shade is from the trees. And all the way on the right over there, I take a picture from underneath the canopy to see how much of the sun the leaves would block out, and they did block out a good amount, which is a good thing. That's what the trees are supposed to do, but they can't do their job if they're dead, like most of them up there. So you can see that a lot of the trees in the area are dead. So the tree map, if you look at the tree map, it tells you when the last time the trees were like checked up on, and most of them is like 2016. It's been a while now, which is understandable, but still an issue. And now going into 4 p.m, you can see that as the sun switches, all the trees, they start shading the street instead of the sidewalk, and the building takes over and shades the majority of the block. See in the left picture, if you look far away, there's a man sitting there resting in the shade. That's one of the behaviors we observed. So people were working, he was working unloading a truck for a while, and rather than just wait or sit in the truck for a little bit, no, he chose to go to the place where there's trash everywhere because it has shade. So people would rather go into shade and risk that uncleanliness instead of sitting in the back of the truck. It's so unclean.
Again, this is just a shade coverage map, so you could see at 12 p.m. how the trees are shading the area. And then in blue at 4 p.m, all the shade is coming from the building.
And foot traffic patterns, average foot traffic at 12 is 8, and at 4 it's 6.5, so it did drop a little bit. Again, people working and resting in the shade provided by the buildings in the tree canopy, and most people just choose to walk around the shaded street. I saw 3 people during their lunch break choose to walk down that area.
This is unshaded versus shaded surface temperatures at the site. Here you can see the soil retains less heat than the concrete. The air temperature was 96 degrees. And the shaded surfaces are relatively similar temperatures, so you can see the importance of shade in this area. And then again at 4 p.m, a little bit more of a difference, but similar results. Oh, there we are, sorry. So this is our third site and our final site, 49th Street. This site has a lot of vehicles zooming through the street. There's a lot of unloading and loading of trucks. There are 2 very large parking lots, or 3 very large parking lots you can see in this photo. A lot of trucks coming in and out of here. And in this site, we focused on the sidewalk and this little plot of land almost pushed out from the sidewalk, and that is a soil plot.
And again, just the tree map, and you can see that the thornless honey locust tree makes an appearance once again, but it's dead. So looking at the shading in the area, you can see that that little patch provides like a good amount of shade if it was accessible. The problem is that it's so far down that unless you want to go sleep under there or crouch and walk through it, you can't really do much. We saw a cat under there walking, so, and a few geese walking by, so at least they get to get some shade. But yeah, and while the top right over there, while that wasn't part of our study area, those trees did provide some shade at 4, but like right now they provide like no shade at all. It's all the shade is on the other side of the fence where no one can access it. So it's pretty nice. And see now at 4 p.m. as the sun switches angles, now there's no shade at all that you can access. If you even were to crouch, you literally have to press up against the wall and just sleep there or something. But yeah, now there's no shade that much, and that little patch of soil all the way back there, unless you want to climb up there and sit there,
There's basically no shade anywhere there.
no shade.
You'll see in the map, so you see the soil plot at 12 p.m. that shade is not accessible anyway. But at 4 p.m., there is virtually no shade. It's essentially shade coming from a little fence that fences off the area. So there is virtually no shade that is accessible to people. And it is a very overgrown walking space that, with a little help, could provide a lot of very useful shade for all the workers in the area.
And foot traffic pattern. You see this is probably the most drastic difference. 9.5 at 12 p.m. and 3 at 4 p.m. People working and unloading trucks again, and the pedestrians were mainly walking on the other side. And it would be a good thing if the trees actually provided shade, but no, neither of the sides really has much shade. And when we see like the drop at all three sites at 4 p.m. going in, we were like, okay, 4 p.m. is peak hours. That's when a lot of people would be leaving work. But sadly, it didn't turn out that way. Most likely that's because people started leaving after 4 p.m. and maybe a little earlier. There's a lot of things that could have went into that.
We also think it might be because people might have been in cars. So all the cars we see rushing down the road, those are potential foot traffic people that were not foot traffic. So here you see unshaded versus shaded temperatures once more. The unshaded concrete is significantly higher than anything else, than the shaded soil or even the unshaded soil. So if you imagine the shaded concrete, that is the concrete that is all the way pushed under the vegetation. So that concrete is basically shaded the whole day. We can't access it, but that concrete is very cool because it's not getting any sun all day. And the air temperature here was 94 degrees. So the concrete was well above 100. And you can once again begin to understand how important shade is in this area. And then again, 4 p.m., even less shade, so temperatures begin to rise. And we had several issues with the weather. I won't read everything, but we had to retake measurements at Grand Avenue, which might have affected our data. And there was a lot of rain and cloudiness that affected our shading measurements.
Yeah, originally we wanted to keep it consistent to Tuesdays and Thursdays so we get the same workforce, but it didn't turn out that way. It rained a lot of days, and then the wildfires messed up the air quality, so we wouldn't be able to get accurate measurements for that.
So conclusions and discussions. Heat is very deadly. The IBC is a very hot place. As we've seen, 2% of warm month deaths are caused by exposure to heat. Extreme heat events in New York City kill more people than any other extreme weather event, which includes things like hurricanes and flooding, which when you think of extreme heat event or extreme events in New York City, that's mainly what you think of. You don't think of heat. It exacerbates pre-existing respiratory conditions like asthma and COPD, which already occur at greater rates among industry workers. And also, heat is just really unpleasant to work in. We were out there all the time in the heat. It was not nice. You're sweaty, you're dizzy. So if you just imagine someone who's working with heavy machinery in these kinds of conditions, it really affects the work quality and the work safety. So what is the point of this presentation? We throw all this really scary information at you. And these are just headlines taken from like a single week, maybe 2 weeks. It felt like the world was on fire, but we don't mean to scare you. We'd like to, no pun intended, light a fire underneath you. So we hope you can take these main takeaways and go out into the world and combat UHI. So heat is essentially a very pressing threat, as we've seen. In our city, especially in the IBZs, there's an abundance of dark, barren surfaces. It makes heat very intense. We saw the asphalt, we saw the concrete being significantly hotter. And then shade and canopy coverage, as Mohamed was talking about shading trees. Excuse me. Canopy coverage is really important because you could also see in the graphs how much hotter unshaded surfaces were than shaded surfaces. And the people working in these areas are often part of very vulnerable groups. So it's very important that we combat UHI in a way that benefits them rather than hurts how they work or affects their work quality. And we would like to argue that our 3 sites are prime examples of opportunity, and there are plenty of sites similar to them within the Maspeth IBZ to incorporate green space into, if we just look. And that's our references. Thank you very much.
Hi, my name is Darius Korin, and I did my study on the urban heat island and soil degradation. What is an urban heat island? Once again, an urban heat island is an area that has increasingly high temperatures compared to its surrounding rural areas. Heat created through heavy industrialization and emissions builds up over time and is usually able to be dispersed through green spaces and plants' natural cycles. However, due to the dense proximity of buildings and surfaces like asphalt, metal, and glass, those materials act as insulators and actually retain the heat. And pairing that with a lack of green space, we have UHIs. So how is soil specifically impacted by urban heat islands and industrialization? Over here is just another temperature map. And you can see Maspeth and Greenpoint industrial zones right here. This is Maspeth right there. So our 2 main points are extreme heat and runoff. Extreme heat, higher temperatures leads to higher rates of evapotranspiration, which is the plant cycle where they intake water through the soil, through the roots, and through transpiration, turn that liquid into gas, which is water vapor. And then, however, if these rates are too high, then the soil will dry out, and dry soil leads to low nutrient levels. Runoff is a big problem, especially in urban heat islands and industrial zones. When rainwater is heated on surfaces like metal, some of those particles and toxic debris flake off, creating a toxic runoff. Additionally, due to the majority of land usage being these impermeable surfaces like concrete, asphalt, this toxic runoff from industry goes to those few green spaces. Specifically, concrete particles that get caught in runoff can affect soil pH, increasing those levels dramatically. Oh. Okay, green space mitigation. This is another map of kind of a satellite view of green spaces in New York City. Not a lot, very sparse, especially looking at those industrial zones. Green infrastructure is an essential way to mitigate urban heat islands. Trees act as green canopies, providing shade and protection to soil from those dangerous UV rays. And then plants intake heat and release moisture into the air through evapotranspiration, creating a cooling effect. So kind of acting as a natural air conditioner for its area. And then plants are also wonderful at absorbing air pollutants and seclude CO2, which is one of the top pollutants found in industrial zones. Also through rain gardens and just general green infrastructure, their ability to hold stormwater runoff and filter out contamination is also very important. So what were my goals in this study? I wanted to do a general research study to understand the soil quality of Maspeth IBZ, specifically observing how urban heat island affects soil quality. And through that, I want to compare and look for trends and differences between soil plots. So is there a difference in rate of soil degradation between these spaces? And those spaces being, which I'm going to get into right now, maintained green spaces and unmaintained green spaces. So my hypothesis is that maintained green spaces experience lower rates of soil degradation. And therefore, by creating more maintained spaces, we can help mitigate urban heat island in Maspeth IBZ. Okay, so just a little bit of very brief background on my sampling. In the red here is our study zone of Maspeth IBZ, and all these points there are places where I sampled. You obviously notice the two different colors. We have our 8 points in blue, which are our unmaintained sites, and then our 2 little green trees are our maintained sites. And I chose these sites, all 10 of them, because I wanted to get a diverse range of soil in Maspeth IBZ. So what are the differences between these 2 soil plots? Here's me digging in an unmaintained site, and this is our Plank Road site, which is our maintained site, one of them. So maintained soil plots are developed green spaces with green infrastructure. That includes native flowers and plants, green canopies and shading, and some maintenance, trash cleanup, planting, stuff like that. Unmaintained soil plots. It is possible to climb up there. That is the there's third point. But unmaintained soil plots are often overgrown with invasive weeds and plants. There's little to no green canopies or shading, as we learned from that specific spot. And there's no maintenance, and often are found to be littered with trash and dumped. Data collection process. So what I did was I went to each of these 10 sites and dug different soil holes. When you're doing soil sampling, the best part is just digging holes. So I dug around 6 to 10 inches deep, bagged and labeled with date, location, and took notes on weather conditions. So these are our 2 days, the 19th and 20th. The 19th was a humid, partly cloudy day. And there was previous rain during the night and briefly in the late morning to mid-afternoon. And then when soil was collected in the later afternoon, it was partially damp, but mostly dry. And then from the 20th, it was a very dry, hot, and sunny day, and the soil collected then was very dry. Testing process. So I tested for 3 things, which were heavy metal contamination through XRF X-ray fluorescence testing gun, which is a kind of like how a heat gun is able to pick up heat. This is able to directly give you heavy metal readings. Shout out North Brooklyn neighbors. They helped me with that testing. But it's a great way to kind of avoid having to go to labs, because historically, when you want to get this done, you have to send your samples in for labs. It's expensive, so we got to avoid that, which is nice. General soil nutrients, testing for nitrate, phosphorus, and potassium through an NPK soil kit, and then soil acidity through soil pH testing. Yeah, I'm wearing the same exact outfit. Don't let's not, this didn't happen today, so just bear with me. So this is my heavy metal testing. The goals of this test was to identify which specific metals are present in soil. And is there a difference in this contamination between our maintained and unmaintained sites? So what are we specifically looking for? So our main heavy metals that we're looking for are lead, zinc, copper, manganese, and arsenic. So we're looking for lead specifically, anything above 400 parts per million, which is considered toxic. Zinc, anything above 150 parts per million, toxic. Copper, 50 to 150 parts per million. Manganese, more than 400 ppm and arsenic above 16. So this is what we found in data from that I sampled from the 19th. There is a lot of contamination in the soil. We will get to this number. But as far as lead, there was way over 400 parts per million lead in samples 3, 4, 5, and 6, 4 being one of our maintained sites. So keep note of that. And the rest are unmaintained sites. So samples 4 and 9 are our maintained sites. And then for zinc, there was over 100 in all of them. And it was very extreme in 3, 4, and 6, again, hitting that maintained site, which is contradictory towards what my hypothesis was. And then copper was noticeable in almost all of these. And then we have this huge peak. Remember, our original range was 50 to 150, but at soil sample 0.3, we registered 4,110 parts per million, which is wild. And then manganese, we're looking for above 400 parts per million, which was in samples 1, 2, 3, 4, 5, 6, 7, 8, and 9. Yes. And then here's our data from the next day. We're still seeing those similar trends. However, there is more, I guess, disparity up between these. So lead, again, visible in samples 0.4, which is our maintained site, 5 and 9, which is also our maintained site, and then zinc in all, and then copper, again, high in this sample 2, but not as high as it was before, and then manganese in basically all of these. For some reason, it didn't let me add arsenic for some reason, but there was a little bit above the 16 range for soil sample 9. So just want to put that out there. So why might this be? So just a little bit of historical context for contamination. This is Phelps Dodge copper refinery. It was a copper refinery that had a very big impact in Maspeth, Queens, and that industrial area. Originally, it was Laurel Hill Works, which I believe started in 1908, if I'm not mistaken, but specifically Phelps Dodge ran from 1920 to 1983, where through 60 years of industry, it was responsible for dumping and polluting heavy contamination around the area of Maspeth, Queens. A couple things I want to note. So remember our soil 0.3, which had those really high copper rates? Those are actually like right in this area, which is like basically part of the copper refinery. So 60-year-olds, at least 60-year-olds, no, over 100 actually, over 100 years of contamination still is in this area, and still present within all of these sites in Maspeth. So this is kind of like an overview. I'm really new to Photoshop, so bear with me, but this is some aerial footage of the Maspeth IBZ from around 1940. And then this is it overlaid with some of my soil sampling plots. So you get another visual of what used to be there and what it was now and then. Specifically with this green space, I don't know if you can see it. It's right there, which is probably around like right here. There was just like it was just the whole factory on top of it. So it wasn't a green space for all of its entirety. So that's another thing to keep in note. All right. So our next test was our nutrient NPK testing for nitrate, phosphorus, and potassium. Basically just determining nutrient level in soils. And again, the question, do we see an increase in soil nutrient quality in maintained and developed green spaces and vice versa? So what are we looking for? Nitrogen levels, which are essential for developing plant structures, phosphorus, which is important for cell division and general plant growth. And then potassium is essential for building that root structure and for drought resistance. However, excessive amounts of any of these nutrients can deplete the nutrient intake of others. So, for example, excessive potassium can lead to clogged pore space, inhibiting water distribution. So these are our NPK soil results. The test I did, as you can see, it's a color chart. So really wasn't given too many units, so I made my own kind of. So this is the scale of 0 to 12. So 3 being our medium, 3 being our low, 6 being medium, and 9 being high. And then anything above or below those points are either depleted or excessive. So just taking a look at that, we see that most of these samples are depleted and have low levels of nitrogen, with the highest soil sample 9, just above low, which still isn't a lot, but it is larger compared to the rest of the sampling. So soil sample 9, which is one of our maintained sites. Phosphorus registered mostly above medium, with samples 2 and 4 registering at 8. So again, one of our maintained sites, which is good news. So that blue mark right there, and this one right here, so sample 2, both registering at 8, which is a pretty solid number. And then potassium. This one was interesting. Potassium was found to be excessive, peaking as high as 12 in sample 2, but was like lower than that for the rest of them. But still, a lot of these points, above 9 are going to be excessive. So we did see a lot of potassium that could be resulting in the other nutrients not being able to be present. And then this is our other one. Oh, sorry, the last test was from the soil from the 20th. This is from the 19th. So as you can see, we have higher nitrogen, phosphorus, and potassium nutrients found in soil points 4 and 5, with the rest of the samples showing depletion and or excessive nutrients 4 or 5. Sorry, I meant 4 or 9. Sorry. So as you can see in our samples 4 and our samples 9, we have the highest level of potassium and also some of the higher levels of nitrogen, and then lower levels of potassium, which is good. And then lastly was the pH testing. So the goal of this testing was to identify where we see elevated pH levels, and then compare our 2 points, maintained and unmaintained. So what does low/high soil pH indicate? Low soil pH under 6.5 indicates high acidity in soil. And then an optimal range for pH is around 6.5 to 7.5. And then high and excessive soil, which is above 7.6 pH, indicate strong alkaline soil, which is notable in soils that receive little rainfall, have poor water distribution, and make it hard to intake essential soil nutrients. So again, seeing a comparison and overlap between nutrient testing and pH testing. So what do we find? So neutral to mild alkaline levels in soil samples 1, 3, and 9, which is good. So sample 1 registered 7.6. So in that pretty decent range. 3, 7.5, and then 9, 7.6 again. And then higher pH levels, which is not necessarily what we want. In soil points 2, 5, 6, 7, 8, and 10. So yeah, this is a problem because a lot of plants kind of need a little bit of acidic soil for them to survive. And most plants actually need that optimum range. Conclusion. So soil nutrient quality is overall poor and toxic in the IBZ because of urban heat islands and historical pollution. However, to look on the bright side, the soil nutrient and pH tests, we observe better results in our maintained soil plots 4 and 9. And when it comes to heavy metal contamination, it's really hard to pinpoint the source for contamination, whether it's recent or historical. But we must take into account that historical use of industry. And hopefully for the future, we can use this data to get a general understanding of soil degradation in the IBZ and promote green infrastructure projects. So this data may suggest that developing green spaces, they will perform better and become more prosperous in an IBZ and can help mitigate UHI. So yeah, and these are my references. Thank you.
Like this, the last tab, it's like, let me just right now, but we're there.
Oh, cool. Good. So hi, good evening. Thank everybody for coming. So the thesis of my research was examining green infrastructure connectivity in the Maspeth IBZ and looking to enhance the ecological resistance, livability, and mitigating the urban heat island effect. My research question is, how can we visualize the connectivity of green infrastructure in the IBZ? So you guys already got a lot of definition of UHI since I was going last. I kind of skipped over that, going straight into my topic. So my topic is an intersection of urban planning and environmental sustainability by studying green infrastructure in the area, locating where in Maspeth IBZ the lines can effectively integrate green infrastructure like rain gardens, parks, and tree pits, and also to promote ecological resistance, enhance the livability of the workers and people there, mitigate the UHI effects, and most importantly, generate a connectivity between the GI. So the way I went about it was, one, I wanted to create maps. That was my deliverable. I did a lot of field work by looking at the GI myself, went around, saw big disconnectivity, and then I was straight into the data, and I did a lot of research on New York City open data on the GI in the area. The tools I used was ArcGIS Pro, which was not fun, Google My Maps, and New York City open data. So the first map I made was pretty simple, which to just locate the green infrastructure in the IBZ. So this is the creek right here. That's Queens. That's the Brooklyn border. It's down here. And you can see there's not much. The whole southwestern portion of the neighborhood is just completely isolated. And there's 2 undeveloped spaces, which is Plank Road and the site next to the DEP pump house, and just very few little trees. Anything, the northwestern part had way more GI compared to everything else. And there's still some cluster over here, but for most of the part, for most of the matter, there's barely any GI, and this map can help visualize that. 2 of the data sets that you can see on this map are the city benches and the public water fountains, because there are none. But I thought it was cool to include. There actually is a city bench like right here, but it's just one and it's kind of outside the zone. It's near school. So moving on, I started playing with the data and try to find all the disconnectivity that I could through some of the different layers. One these two layers specifically are the sidewalks that exist in the area, which is represented by the black, and then the DOT pedestrian mobility plan, which is represented by the yellow. So everything in red is where there isn't a sidewalk that could be a sidewalk. So I found about, what did I have here? 31 disconnections. So about 31 sidewalks that don't exist that can really help with pedestrian mobility in the area. It's just one way to use a map to help visualize this disconnectivity. And then this one has overall the connectivity between all the GI. So I included bus routes and the bus stops. And as you can see, and like Alexis and Mohamed talked about, there's only, well, they said there was 4 routes. According to my dad, there was 2. Maybe should have talked to him about it, but I found 2 bus routes and about 27 bus stops. And I could, the data on the bus shelters wasn't loading for me, so I couldn't load that up. But as you can see, if you had to take the bus, this whole area over here is basically inaccessible. You have to walk, or, you know, like brought up in other projects, a lot of people just end up driving to the area because it's so disconnected. So this was probably one of my favorite maps, which took a while and made my computer almost die. It's the density of all the GI data in the area. So the density of the bike lane, the trees, and the DEP green infrastructure, which is the rain gardens, unused space that could totally be used because it's just green space that's just sitting there. But this map really shows that it's just completely disconnected. It's just a lot of open space. That's just the built environment that's causing this UHI effects more. So how do we fix the disconnection is the question. So from here is where I was doing a lot more analysis with my data, but at this point, my computer kept crashing. It was really bad. I would have loved for this to have been much more developed than I would have wanted. I proposed water fountains, more city benches, a lot more bike lanes. But I was able to show proposed new parks, which is one of the NCA vision plans down by the copper refinery that Darius was talking about. And then that Plank Road, and then also the unused developed space, underdeveloped space next to the DEP pump house. And then one thing that I also, I couldn't really get the attributes because my computer was running really slow, but it was something like, I think 150 more trees. And I think it was like 100 more rain gardens, something like that. And you can also see when I first started doing this research, I looked at Google Maps and an overview, and I saw there's no greenery. Reason why it's such a hotspot. And I saw that the railroad was it looked like it wasn't in use, but when doing a lot of field work, I realized it was. The Department of Sanitation uses it for trash trains. So, and some of the industrial businesses still use it, but not much. It's mostly used by Department of Sanitation. But this whole railroad runs through the IBZ down more south into Brooklyn and back out into Western Brooklyn. So in my mind, I was like, if we can make a bike trail in the middle of this neighborhood, we could increase the GI connectivity much more, especially if we implement all the other things that I said, like trees, water fountains, and rain gardens. So I wanted to put that all on one map and then take each layer and show these proposed GI implementations. ArcGIS didn't allow for that, but here I am. This map is from Walk Square. It shows the bike residents that the commuters, the residents that are bike commuters in the Maspeth IBZ, and I thought this was a really cool map for my research, because as you can see by this cluster, it wraps around the whole railroad. So if there was a railroad, this is my proposed map for the railroad, this would be the entrance right by a restaurant depot by the old copper refinery. It would go down a little outside of the zone where there would likely be an A bridge or something to get over the track, because it would still be in use for Department of Sanitation. And then, there's another project out there called the QNS project that wants to use the railroad for light commuter railing as well as a bike trail. So a bridge proposed so that the train can still keep running, and then back out into more East Williamsburg, a little more outside of the study zone where it would end, which is over here. And yeah, I think that was kind of my project, to get maps, visualize the disconnectivity, and then use these maps to visualize implementations for new GI.